Good day, viewers all over the world. My name is Dr. Chris Esekaibe. I welcome you to class today. Today, we are having a special topic. We shall be looking at the Newton's generalized method for finding a real root of an algebraic stroke transcendental equation. We were able to look at the Newton-Raphson method in one of our videos, but today we shall be looking at the Newton's generalized method. Beloved, I'm the owner of this YouTube channel. I am a chief lecturer in one of the most prestigious polytechnics in Nigeria. I work in Nigeria. I live in Nigeria. I am a mathematician. I'm also a statistician. I train AI models. I lecture in the Polytechnic, and I've attained the highest position, which is the position of a chief lecturer. By the special grace of God, I hold a doctorate degree in mathematics with distinction from a renowned university. I also hold a master's degree and a bachelor degree in statistics. My master's degree is in mathematics. I specialize in numerical analysis, data analysis and modeling, scientific computing, and statistical analysis. I've been privileged to work with 2 AI firms in the United States of America, where I assisted in training AI models. What I do, I create prompts to break the model, to stomp the model. Then at the end of the day, if the model is unable to give the right response, I will now create rubrics, create chain of thoughts, and also create golden responses that will be used to train the model. If you are an AI firm, I'll be looking forward to hearing from you. If you are also a research firm, I can be part of your research as a statistician and a mathematician. And also, if you are a research student, maybe an MSc student or a PhD student, you can also contact me or consult me. Your consultation is free. I don't collect any charge from postgraduate students, from any students all over the world. So your consultation is free. I've attended to students from Malawi and Uganda. So if you are doing, like one was doing masters in mathematics, his area of specialization is numerical analysis. Another one was doing masters in statistics, and I also assisted in one way or the other. My contacts are here on the board. The first contact is +234 80 21903. The second contact is +234 7066 297535. This first contact is for WhatsApp and call, while the second contact is only for call. Then my email address is given, chrisdavids2015@gmail.com. Don't forget to add this S, it's chrisdavids2015@gmail.com. So I'll be looking forward to hearing from you. And today we are looking at a special topic. Permit me to claim my contact so that we can go to the business of the day. We are looking at a special part of numerical analysis. This is a special part of numerical analysis. We have been able to solve algebraic and transcendental equations using various numerical methods. We use the method of first position, the bisection method, the Newton-Raphson method. Today we are looking at the Newton's generalized method. The Newton's generalized method. The Newton's generalized method is given by this formula with multiplicity P. This P here is a multiplicity. P is a multiplicity. This makes the general Newton's formula to be quite different from the Newton-Raphson formula. Now, this formula reduces to the Newton-Raphson formula. It reduces to the Newton-Raphson formula when the multiplicity P is equal to 1. When P is 1, this particular Newton's generalized formula will be reduced to the Newton-Raphson formula. Now, it is good for us to understand that the Newton-Raphson formula, of course, converges faster than other methods or other formulae that were considered. Now, let us see how this Newton's generalized formula works. Now, let epsilon be a root. Let epsilon be a root of f of x is equal to 0. You know, this is the standard format of the problem that we solve with multiplicity p. With multiplicity p. Then it follows that epsilon is also a root of f prime of x equals to 0. That is what it means. It follows that epsilon is also a root of f prime of x equals to 0 with multiplicity p minus 1. And of course, epsilon will also be a root of f prime of x equals to 0 with multiplicity p minus 2. And of course, epsilon will also be a root of f prime of x equals to 0 with multiplicity p minus 3, and so on and so forth. So if it is the fourth derivative, then it will be p minus 4, and so on and so forth. So epsilon is a root of this equation. The equation can be a transcendental equation or an algebraic equation. I hope you know the difference between an algebraic equation and a transcendental equation. A transcendental equation may involve trigonometric functions or exponential functions, but the algebraic equation involves only the polynomial. So, and of course, the right hand side must be equal to 0. So, if epsilon is a root of this particular equation, then the multiplicity will be p. If epsilon is also a root of this one, that is the first derivative of this particular equation, the multiplicity will be p minus 1. You can see first derivative p minus 1 multiplicity. Then if it is the second derivative, if epsilon is also a root of this equation, that is the second derivative of this, of course the multiplicity will be p minus 2. So if it is third derivative, the multiplicity will be what? P minus 3, and so on. And so on. So it continues that way. So hence we have these expressions. These expressions will now be useful to us. Hence we are going to have this x naught minus p f of x naught all over f prime of x naught to get the first iteration. Then it continues like that. We can still have x naught minus, of course, when it's now p minus 1, the numerator will now be the first derivative. You can see when its first derivative is p minus 1 multiplicity. So it will be first derivative of x naught all over, of course, it will now be the second derivative of x naught. Then if it continues like that, then you can also have x naught minus, if it's now p minus 2, if it is p minus 2, of course, it's second derivative. So it will start from the second derivative. It will now be f second derivative of x naught all over f the third derivative of x naught. That is how it goes. It continues like that. So if like look at it now, when the multiplicity is p, is f of x naught equals 0. When the multiplicity is p minus 1, is f prime of x naught equals to 0. When the multiplicity is p minus 2, is f prime of x naught equals to 0. When the multiplicity is p minus 3, then of course you have the third derivative of that function equals to 0. So this will now result to this expression. To get the first iteration, we are going to use x naught minus p. Of course, it's starting from the f of x naught all over the f prime. Then if it is p minus 1, of course, it's starting from f prime all over that of the second derivative. Then if it is p minus 2, it's starting from the second derivative all over that of the third derivative. So if all these are solved, we are going to have the same value if there is a root with multiplicity p. So we are going to have the same value for the root if there is a multiplicity p, provided that the initial approximation x naught is chosen sufficiently close to the root. So this is how the Newton's generalized formula works. So now we are going to pick a particular problem to solve, and we are going to see how we can solve this using this particular explanation. Permit me to click what we have here on the board so that we can go ahead and solve a practical example and see how this Newton's generalized formula is applied. It is very simple to apply. Now, this is the example. The example says, find the double root, find the double root of the equation, double root. If it is a double root, of course, it simply means that our p will be 2. So the equation is given as f of x is equal to x cubed minus x squared minus x plus 1 is equal to 0. Of course, the right hand side must be equal to 0. The equation is f of x equals x cubed minus x squared minus x plus 1 equals to 0. Now, for us to choose our x naught, we must know where the actual root lies. The actual roots, now the actual root is 1. If you look at it, f of 1 is equal to 1 raised to the power 3 minus 1 squared minus 1 plus 1, and that 1 minus 1 is 0, minus 1 plus 1 is 0. So this is the actual root is 1, is unity. The actual root is unity. So we have the choice to choose an initial approximation. So we choose an initial approximation x naught to be equal to, now we can choose a value around 1. Somebody may decide to choose 0.9, another person may choose 0.8, another person may choose 0.7. But now that we have been guided that the root, the actual root is 1, so let us choose our x naught to be equal to 0.8. So we have chosen it and it's closer to the root. Now we want to see how we can use this generalized Newton's formula to solve this particular problem, to find double root. So from this case, p is equal to 2 because we are told to find the double root. So our P is 2 because it's from the word double. So since our P is 2, now we are going to make use of two of those approximations that were solved. Remember, that means we are going to make use of xn plus 1 is equal to xn minus p f of xn all over f prime of xn. We are going to use this to get the first root because we are looking for double root. Then the second one, we are going to use xn plus 1 equals xn. Remember, this is p, the multiplicity. If we put it as p minus 1, of course, what will now be the numerator as explained when we were explaining the generalized Newton's method. If it is p minus 1, of course, you know this will start from f prime of xn all over f prime prime of xn. Now, if p is 3, for instance, if the multiplicity is 3, or we are told to look for triple root, then the third equation will be needed. Each of these is expected to, if we have an initial approximation and the multiplicity p, each of these is expected to produce the same root. So now, if there is a third one, for instance, we are going to use it as this xn plus 1 will be xn, of course, minus this one will be p minus 2. You can see now. Then, of course, if it is p minus 2 as explained, this one will now start from second derivative of xn all over, of course, this will now be the third derivative of xn. But this one will not be needed because we are only told to look for double roots. So this and this will form the double root. If you want to get a fourth equation, you can go on and on and on. The fourth equation will be p minus 3. Of course, that will start from the third derivative all over the fourth derivative, and so on and so forth. So this is the Newton's. If it is the fourth one, fourth root, it will be xn plus 1 is equal to xn minus, of course, this will now be p minus 3. Then this will now start from the third derivative because it's p minus 3 all over the fourth derivative of that, and so on and so forth. So now, since it is just the double root, we don't need this. We only need the first two approximations to get the double root. So these are the two formulae we are going to be using. So it is good you have a better understanding of that. Now remember that our f of x is equal to x raised to power 3 minus x squared minus x plus 1 is equal to 0. Now, if you look at these two formulae, we need f prime of xn, we need f prime here and f prime prime. So now, for us to get our f prime of x here, I'm going to differentiate this with respect to s to have the first derivative. So this will now be 3x squared. If I differentiate s cubed, 3x squared minus 2x minus 1. That is that. Then, of course, if I now want to get my second derivative going to be needed here, that will be f prime prime of x. Of course, I will now differentiate 3x squared will be 6x. Then if I differentiate minus 2x, I will have minus 2, of course. Differentiating 1 will be 0. Here, differentiating 1 also will be 0. When you differentiate a constant, you have 0. You differentiate a constant with respect to a particular variable, you have 0. Now, we can start our first iteration at n is equal to 0. Remember, our x naught is 0.8 as chosen because the actual solution is unity. So, if we have this, that means, yeah, from these two formulae, when n is 0, here we are going to have x1 equals x naught minus, what is our p? Of course, our p is 2, which is the multiplicity, minus 2, then, of course, f of x naught all over f prime of x naught. This one is for the first root. Then for the second root, when n is 0, this will be x1 will now be equal to, of course, n is 0, x naught. P is 2, 2 minus 1 is 1, so multiplication by 1 has no effect. Then here you are going to have f prime of x naught, because our n is 0, then all over f prime of x naught. That is what we are going to get. So by the time we have this, you will see that we need values for f of x naught, f prime of x naught, then f prime of x naught. Permit me to clean the question. I hope you are taking note of the question. We are to look for the double root. So permit me to clean this part. Permit me to clean this part that we have written. So that we can have some space to solve and get what we actually want. So if you come here, of course there is a square here. Now if you come here, we have to continue. If we want to get our, now let's get our f of x naught, which will be equal to f of 0.8. So anytime we are talking about f, we are talking about the main function. So our f of x is this, so our f of 0.8 will be equal to 0.8 raised to the power 3 minus 0.8 squared minus 0.8 plus 1. So you use your calculator. 0.8 raised to power 3 minus 0.8 squared minus 0.8 plus 1. That would be 0.072. 0.072. Then of course we need to get our f prime of x naught. That will be equal to f prime of 0.8. And now when you are talking about f prime, this is the formula for f prime. So this will be 3 into 0.8 squared minus 2 into 0.8 minus 2 into 0.8 then minus 1. So you use your calculator. You know this is numerical analysis. It is good you make use of your calculator. You are going to get minus 0.68 minus 0.68. Then lastly, we need to get our f prime, that is the second derivative of x naught, and that will be f prime of 0.8, because our x naught is 0.8, and we are talking about f prime, we are using this. So that will be 6 into, of course, our x naught is 0.8 minus 2. Then by the time you use your calculator, 6 into 0.8 minus 2, you are going to have 2.8. So that is what we are going to have. So now, coming to this, we are going to have, we want to use this first formula. Here, our x1 will be equal to, what is our x naught? 0.8. Then minus 2 into, what is our f of x naught? Our f of x naught is 0.072 all over. What is our f prime of x naught? F prime of x naught is minus 0.68. Then of course minus here will now become plus. Minus will now become plus. So you are going to have 0.8 plus. Of course you use 2 to multiply this and divide it by what you have here. You are going to have 0.211,765, and that will give us a total of 1.012. That is what we are going to have, 1.012. You carry out that addition. Then let us use this second one. Here our x1 also, because we are getting the double root. x1 is equal to, of course, x1 is equal to x naught is 0.8 minus, of course, f prime of x naught. F prime of x naught is minus 0.68 all over f prime is 2.8 all over 2.8. That will be 0.8 minus will become plus. It will be 0.8. By the time you have 0.68 over 2.8, you are going to have 0.242857 plus 0.242857. 0.242857. By the time you carry out the addition, you are going to have 1.043. So we are gotten the double root at the first iteration. Please take note of this. We have gotten the double root at the first iteration. So we are going to now let me clean this part, because we are going to use, you can see we are going to still use these values. Now you can see from what we have here, our x1 is 1.012 for the first root, and our x1 is also 1.043 for the second root. Now we have gotten the double root. It is also important that we see how we can go ahead to get x2, because at each iteration we are going to get double root. So now our actual root is 1, but now we have two roots. The first one is 1.012, the second one is 1.043. Now how do we choose? Now we want to take the next iteration here, n will be equal to 1. How do we now choose? Which one do we now choose? We are going to choose, listen, we are going to choose from these two values, the one that will represent our x1, so the one that is closer to the actual root. Remember, our actual root is x equal to 1, and this one is closer to 1 than this. So we are going to choose our x1 to be equal to 1.012. That is what we are going to use. So if we have that, then of course we remember the generalized Newton formula. The generalized Newton formula, permit me to write it here, is xn plus 1 is equal to xn minus p f of xn all over f prime of xn. That one is for the first one. So now we want to get, from here we want to get our x2. Our x2 will be equal to x1. Of course, we are using the two values. So if it is the second one, we are going to use xn plus 1 is equal to xn minus p minus 1. Then f prime of xn. This is f prime of xn all over f prime prime of xn. So these are the two formulae we are using to get the double roots. So the closer, this one is closer to the unity, so that is why we are choosing it as the x1. So from here now, to get our x2, when n is 1, 1 plus 1 is 2. So of course our multiplicity p remains the same, our p remains 2. So this will be x1 minus, what is our p? Our p is 2, then f of x1 all over f prime of x1. That's for the first root. Then for the second root, we have x2 will be equal to x1, of course 1 plus 1 at the first iteration, and 1 plus 1 will be 2. Then xn, n is 1, of course minus p minus 1 is 1, that is 2 minus 1. Then of course minus f prime of x1 all over f prime prime of x1. So this is now the formula we are going to use to get the double roots for the second iteration. So permit me to clean this part again. I hope you have seen the first iteration, the double roots we got. We got 1.012 and 1.043. So permit me to clean this part so that we can work with the second iteration and see if it will converge to the actual root. The actual root is unity, is 1, so we will now see if it will converge to it. Now, okay, let me also clean the question so that at the end of the day, we'll be able to see, since you have gotten what the question is all about. So coming here now, of course, we need f of x1 here, we need f prime of x1 here. Of course, we also need f prime of x1 here. We also need f prime of x1 here. So let us take f of x1 will now be equal to f of 1 point, look at our x1, 0, 1, 2. So anytime you're talking about f of x, which is the mother equation, that is the problem, then you are going to have 1.012 raised to the power 3 minus 1.012, of course, square, minus 1.012 plus 1, and that is what? What are we going to get from there? We are going to get 0.000289,728. 289,728. That is for that. Now let us get our f prime of x1, and that will be f prime of 1.012, and that will be equal to, anytime we are talking about f prime, this is the equation we are using. So this will be 3 into 1.012 squared minus 2 into 1.012, 2 into x, of course, minus 1. Then we carry out, of course, an equation sign. Then let us carry out this simple arithmetic. So 3 into that square minus 2 into that minus 1, we're going to have 0.0484, 0.0484, 32. Then let's get for the f prime of x1, and that will be equal to f prime of 1.012. Of course, anytime we are talking about s prime is 6x minus 2. So that will be 6 into 1.012, of course, minus 2. Okay. Then, of course, we have our equation sign. If you carry that out, you are going to have f prime of 1.012 to be 4.072. That will be 4.072. So you can see how we have been able to get this. So now putting these values in, you will come here and have your x2. Your x2 from here will now become, what is our x1? 1.012. Then minus 2 into, what is our f of x1? Look at our f of x1, 2 into, our f of x1 is 0.000289,728 all over. What is our f prime of x1? Of course, is 0.048432, and that will be equal to 1.012 minus what? When you carry out that, you are going to have 1.012 minus 0.0 minus 0.011 minus 0.0119643, 9643, and that will give us 1.0000, of course, up to 4 decimal places. You can see. Then let's use the second one. Our x2 is equal to, what is our x1? 1.012 minus, what is our f of x prime? That is 0.048432. That's our f prime of x1 all over f prime is 4.072. That will be 1.012 minus. Carry out this division. It will be 1.012 minus Of course, you carry that out, it will be 0.011, 0.011893991. 89391. When you carry out that subtraction, you are going to have 1.0001. You can see. Now, beloved, at 3 decimal places, it has converged to 1. So you can see that we conclude that therefore that there is a double root at. So permit me to clean this part. Permit me to show you have seen these are the necessary parameters that we use to solve the particular problem. So you come here now, we can now conclude that you can see what we have here. So we can conclude that there is a double root at x equals to 1.000. Let's take it at 3 decimal places of accuracy. There is a double root at, of course, you can put it 3 decimal places. So, of course, which is sufficiently close, which is sufficiently close to the actual root unity. So the actual root is 1. So you can see just 2 iterations. The generalized Newton's method has converged. So we can say the generalized Newton's method converges more rapidly than the Newton-Raphson method. So it converges more rapidly at just 2 iterations. It has converged to the double roots. So you can see it's just 3 decimal places. We solve for just x1 and x2 and double root. So you can see how the generalized Newton's method converges faster. We have been able to come to the end of today's class. Beloved, I know you have learned something new today. The essence of this YouTube channel is to share knowledge in key areas in mathematics, most especially numerical analysis and applied statistics. The essence is to share knowledge in these key areas across the globe. So please, for those of you who have subscribed to my channel, thank you very much for subscribing. For those of you who have not subscribed, who are yet to subscribe, please subscribe and share my videos in all your social media platforms. And as you do, God will bless you richly. Enjoy the rest of the day. Bye. God bless you.